In the previous lecture, we have discussed about the isobaric and isochoric process, and for this process, we have calculated change in internal energy, work done, dq, etc. Suppose we are considering a process in the PV diagram like this. This is PV diagram, and the process is like this. And this is the direction of the process A, B and C. This is a cyclic process. You see the arrow A, B, C. It is going from A to B, B to C, C to A. This is a cyclic process. So if we ask what is the change in internal energy during the process for the closed path ABC, the answer would be 0. du is equal to 0, because change in internal energy in a cyclic process always 0, because it is coming to the same initial state. Suppose we are starting from A, we are going to B, then B to C, and after that we are going from A to B, B to C and C to A. Finally we are coming to the same initial state. So the change in internal energy is 0. Then what is the change in the heat produced during the process? Suppose this is twice P0, this is P0, and initial volume is V0, and at the point C the volume is 2V0. Okay, so you have to calculate dq. As you know, dq is equal to minus dw. So what it would be the value of dw? It is simple the area within the triangle ABC. This is the area of the triangle ABC. So this is minus half P0 V0. This is the work done during the process ABC, and you see here the volume is increased. Volume expansion took place because BC for the process BC, the graph area is large. For the process AB, volume constant, so work done 0, and for the AC process, it is the rectangular area. So in the overall, if we sum, the area under the BC curve is large, so the volume expansion during the process, overall volume expansion took place, and it is work done by the system. And if the process is work done by the system, then it will take energy from outside. For doing the work done, we need energy, and this amount of energy dq is minus half P0 V0. If we reverse the process, suppose the process is like this, changing the direction of arrow A, B, C, same twice P0, P0, V0, twice P0, with same as keeping same A, B, C. Here the work done is dq equal to minus dw, and it would be plus half P0 V0, because the volume contraction took place. The arrow is in the direction. In this direction the area is large, and so the volume contraction or volume is decreased. So the dq would be plus half p0 v0. So be careful about the direction in which the process took place. Now suppose we plot the isothermal curve. This is the isothermal curve for PV diagram for an ideal gas, rectangular hyperabola. PV is equal to constant. Isothermal means temperature constant. If it is performed at temperature T1, if it is performed at temperature T2, so T2 must be greater than T1, and so on. Now for isothermal, PV is equal to constant. That means P dV plus V dP is equal to 0. That means dP by dV at constant temperature is minus P by V, and dP by dV means the slope of the curve. So slope of the curve for isothermal process is equal to minus P by V. Now as we know, dq equal to we can write Cv d theta or equal to Cp d theta. Cv d theta means volume constant, so dq would be Cv P2 V by R minus P1 V by R. V constant. For pressure constant, it is equal to Cp PV2 by R minus PV1 by R. This is the value of Cq, Cp and Cv for isobaric and isochoric process. Now suppose we are doing experiment like this. I am drawing the graph. This is the graph, and A, B, C, D is a process. We are going from A to B, B to C, C to D, and again D to A. You have to calculate the heat taken for the process A, B, C, D, A. A, B, C, D, A. For the process A, B, C, D, A, you have to calculate heat taken. It is a PV diagram. Now heat taken took place. You see, heat, we have to calculate the heat taken during the process A, B, C, D, A. Heat taken took place for the process AB and BC. For AB and BC, heat taken took place, AB and BC. For the process CD and DA, heat rejection took place, and it come to the initial state A. Because for AB process, you see it is at constant volume, so at constant volume pressure is increasing. So to increase the pressure, it will take heat from outside for the process. For the process BC at constant pressure but volume is increasing, the system will increase the volume, or to do the work the system will need heat from outside for doing the work. So you have to calculate QAB. QAB means CV d theta, and if it is V0, if it is twice V0, I am going to next page. We drawn the process like this. Suppose it is V0 twice V0, P0 twice P0, P0, A, B, C, D, A total process. So QAB is equal to CV d theta. That means CV PB V by R minus PA V by R. That means 3 by 2 P0 V0. Q BC is equal to CP d theta. That means CP twice P0 VC by R minus twice P0 VB by R. This constant at pressure is 2 P0, and from this we get 5 V0 P0. So total heat taken is 3 by 2 P0 V0 plus, this is not R, because the R taken, it is experiment is performed for monoatomic gas, monoatomic. So if we put CV value, that means 3 by 2, CV is equal to 3 by 2 R, that the CV is equal to 3 by 2 R, as CP is equal to 5 by 2 R. So R should be cancelled, so it is 3 by 2 P0, 5 P0 V0. So total QAB plus QBC equal to 13 by 2 P0 V0. So in question you in the experiment, in the examination, you should follow the first you should follow the directions, and then you must concentrate whether it is for monoatomic, diatomic gas, and for which process it is taken and for which process it is rejected. If the question comes the amount of heat rejected, then you have to consider CD and DA. As you know, for ideal gas and adiabatic process, PV to the power gamma is equal to constant. Again PV equal to RT. So RT by V into V to the power gamma is equal to constant, and from this we get T V to the power gamma minus 1 is equal to constant. This is true for adiabatic process.